See if it just launches, or do you have to refresh it? Yep, it did. It launched it. Now, is there volume? There's volume on this thing. Okay, so let me see. I don't know. I wish I'd have called them earlier, because then I would have found the solution to this, but hey, it's okay. I'm actually, well, let me move it. Been so long, I don't know where I'm at, but that's the beauty of this thing, is it's easy to find out where I'm at. All I gotta do, go in here and just start stepping backwards. Oh, okay. That has no problem number, but that came from the homework, I think. As did that one and that one. And that's the other class. So we get down to here. Okay. Now I've got to remember, I need to arrange these in the proper way. It says I'm looking for 5 or 6. There's 6. And that's the trusses, and we kind of did those. So let's see. I don't have 7 up, so I need to go get 7. And that. Okay, so there's 7. And 7 is partially, okay, so 7 was partially done. Let me see. No, it wasn't partially done. So we found the reaction loads. We were at the reaction loads. Now we're going to go after the internal loads. So this chapter is kind of like a mind game, or kind of like a game. So what you're doing is you have the surface forces that you might have and the weight forces, but what you're interested in is it going to break, whatever it is. And most of this is going to be beams. So I shouldn't say whatever, I should say kind of beams. So what you got is a beam sitting here. Looks like it's buried into the wall over here. Somebody pushed on it with this and then with this. For some reason, which we don't care why right now. Somebody's asked us, do you think it's going to break right here? And so what you do is, in your mind, it's like a mind game. You erase all of this, and then you replace the presence of this with a load that sits at this internal section to resist these two. So what he does, he breaks it. So B is where he broke it. So he broke it here at B. He basically says, I have a left beam and a right beam. And when you're breaking it, you're always going to have a left or a right. When you break it, what's the internal loads? So what he's got, there are three things you can have. A normal force, which is this one, some sort of what is called shear. So this is what they call a shear force, and this is the normal. And then you'll have some sort of moment. And that's all you're going to have. You're going to have either, it's going to be, in this particular case, he's drawn these in the wrong direction because there's a component pushing this way. I don't know what's going on. Component pushing this way, so there's going to be a component pushing back. So, and that's okay. These are standard directions. I mean, and there's a reason for this. There's a reason that these are the standard positive directions. And believe it or not, those are the standard positive directions too. And I'll try to explain why those are, but for right now, we'll just accept that those are standard positive directions. And then, then when you go down to the next page, of course, I guess because he ran out of page space, he just repeats it. So he says, here's your normal force, and then here's your shear force, which he's going to call that V, and that's a standard definition as well. That's a standard symbol that's used throughout this course and the next course you're taking. And then the moment is this MB, and that's standard as well. You get down through here. Now you can have a twist moment, a torsional moment, but if you think about it, if this is a long rod here, and you can have a bending moment here and here, but if you have a moment out in this direction, it's like torsion. It's like twisting, taking the pin and twisting it, trying to shear it off that way. And here's where he gets into a sign convention. And this is actually more important than he's actually giving you indication, but this is really important. And the reason you'll find out is because as you go into mechanics and materials, you'll find that these are standard definitions for a reason. So here's what he's saying is a positive normal. And I'll go ahead and give you some indication of a little bit of an indication as to a way to think of this. Pointing out, think of it like this here, hang on. Anytime you slice a body, so obviously he sliced it here somewhere. Maybe this is right here, I don't know, somewhere in here. When you slice it in a physical body, there's always a normal direction. So if you think about it like this, a positive normal force lines up with the normal direction. So you slice it over here, you get a little normal pointing out. Just think of it as a porcupine. Wherever it is, there's normal pointing out everywhere. They're just dictating the direction. If this lines up with that direction, it's kind of positive. The shear is a little bit weird. So if you look at it, if you look at a left facing, here's your normal, and here's your normal. It sounds weird, but think of it like this. There's a face direction, and you'll find this out in mechanics material. There's a face direction, and there's a surface direction. Like this is going down, but the face is going out. This is going down, to the left, and the face is going up. You'll notice this is opposite direction of that, and this is opposite direction of that. And you'll find out later in mechanics and materials, this face direction plays a big role in a lot of this. The moments are a little bit easier to remember because it has a physical, physical positive moment would be, now here he's showing that if you put a moment here, it's liable to do like this. And I've seen some textbooks say, it can hold water here. So this would be a positive moment. And so the one that's hardest to remember, I find for most people, is this one. And one way to think of it is, this is the way I think of it, although you may have to abandon this thought later, and that is, if I have a positive normal, think of it like this: X and Y. Then I have a positive, then I have a negative direction as a positive. Now that's kind of confusing to a lot of people, so if it confuses you, forget exactly what I just said and just look back at the drawing. The moments are easy to remember. So let's just, I mean, he has worked examples, so I'm just going to go down and try to find one that's in the set. I don't like the P problem. It's just something about them that bothers me. Let's pick the easy. Well, let's just go ahead and pick this one. Determine the normal and shear end moment forces at point C. So what I'm going to do, let's see. Was that the first page? Yeah. Okay. So we'll drop that thing right there. Shrink it down. Now we got a kind of a cool advantage here, but we'll make use of it in a sec. Well, we'll go ahead and make use of it now. If I'm finding the forces at C, I either have to choose the left side or the right side. Just out of the case of simplicity for me, I'm going to choose the right side. So what that means to me is this. Oh, did I hit the wrong button? It means that I'm going to pick this. Then I'm going to move over here, say right around in there. I'm going to drop that. So actually what I'm going to have is a load here that goes up against this, but I don't know its value yet. So I'm just going to call this BY. Now I go over to the drawing and I'll try to find BY. So this kind of relates back to the last chapter because it was finding reactions on the points, and to start the problem here you got to find the reactions on the point, on the support point, what I meant to say. Here's my AY. Technically I'm supposed to have an AX, but if you sum the forces in the X direction equals 0, there's no force X here and there's no force X there, so you don't have anything. And so that just gives you that AX is nothing. So that's pretty boring. Your next goal is to find, and see, for me, I want to work as least amount as possible. So if I find the BY and then I head off and work over here, I can find the answer without ever finding this. And I'll show you what I mean here. So I'm going to sum moments about point A equals 0. That's point A. And I always pick that as positive just because that's the way I am. So I got to pick this one. Okay, so here we go. I'm going to start in on them. Here's, oh, let's make that a little bigger. Yeah, how about that? That big. That may be too big, but I don't care. So going that way appears to be negative, and it's 12 times that distance. Now, this whole load can be replaced by, and I should have done this beforehand, but I think what I'll do is I'll go back to the book because I've already messed up that part right there, and I'll just grab that picture and pull just the picture over, drop it under it to sort of manipulate it. And then what I'm going to do with the picture, I'm going to come in, I'm going to do this. Let's see, I think I need to do this one. Okay, so I need a new, I've got my scissors, so I'll just go in along in here. And I'm replacing this load. Let's see, I think you have to do a copy here to do this. So I'm going to say this is the same thing as that, with one exception. And that is, let's look at the area under all of this. That area is equal to 9, because that's the distance. And this is times 3. That's 9 times 3. Is that 27? And so that tells you, and right in the center, just so happens to be at C. So right in C, you have the load pushing down of 27. So now, technically, I'm going to do something interesting. What I'm going to do is move the equation set I had from this drawing to that one. So here's what I'm going to do. See, it sounds weird, but here, I'm just gonna move it. Move it to right there. I'll just go ahead and start back over with this. Here's my BY. Here's my AY. I don't have an AX, so I'll just say AX equals 0. So now I'm summing the moments. This one was this. Sum of the moments about A. I've got this 27 goes this direction, which is opposite to that. So that's minus 27 times one of these, two of these, and three of these. So I think that's 4.5. And then I have the final thing, which is BY, goes in this direction around. Okay, so that's 3, and then that's 6. So that gives me, hang on, BY equal to, notice there's a minus and a minus there. So I get 12, 1.5, that's 27, 4.5, all divided by 6, which is a number larger than 1. Well, I can't guarantee that. So 1.5 plus 27 times 4.5. Okay, I gotta put the parentheses. And divided by 6, 23.25. 23.25. Okay, so now I move to my picture. And I can just put 20. Yeah, you can just put 23.25. And now I'm focused on this thing. So what is so bizarre here is, and I guess I'm going to have to take a snapshot of this one and copy it back down, because I've got this force on top that I need to find an area for, and then I need to place it halfway in there. And so that's what I'm going to do next. So luckily, I got the snippet tool still there. Let's see, let me do this. Okay, got my scissors. Just go in here. This time I'm clipping across there. Then I think I do a Control C. I move over here. I'll drop it maybe right there. And it's way too big. Here. Let me try to shrink it to the same size as the other. Maybe about right there. So now I've already forgot what that number is right there, but it apparently is 9. So this is 9. The area of this thing is 9 times 1.5. That's the width there. So that'd be 9 plus half of that. What's that, 13.5? Fix me if I'm wrong. So then I've got to put that right here. Is that 13.5 stuck right there halfway, 0.75 from the left, and well, here, let me just do it this way, 3/4 from the left and 3/4 from the right. So it's halfway in between because it's distributed evenly. Now I'm at the point where I can actually do this. Okay, first of all, I'll do the normal force. That one's pretty easy. So if I sum of the forces in the x equals 0, I get the normal force, and I don't have any other force, so I get nothing. So I'm going to erase that. So I mean, I can put it there, but it's going to make the drawing kind of busy, so I'm going to get rid of it. So there isn't a normal force there. So, and in fact, let me kind of get this equation out of the way and say, okay, it's just, yeah, there's no normal force. But, okay, and here's where you may have to, and if there's nothing wrong with this, having to go back and look at the positive and negative. So if you think about it, I have exposed, here, the right end of this. Let me get all this stuff off here. So in other words, I'm looking, my drawing looks like this combined with this combined with this. I'm looking at the right end. I didn't expose the left end. I exposed the right end. That means positive is going up and positive is making the beam tilt down. Now, initially, you may have to look back at that drawing for a while. Here, I'll change the color so here's my positive shear, and it's good to always draw it positive. And then here's my positive moment. There's my shear and there's my moment. So now all you do, the thing to do at this point is, I don't know which one you want to do first, but you have to sum the forces in the y direction. Whichever one you want to do first, you got to do the moments and the sum of the forces, but we'll do the forces first. So if this positive is up, then I get a V. The shear goes down here. It looks like I get a minus 13.5, and that came from up here. And then I get a plus 23.25. So I get a shear of 23.25 minus 13.5. Almost looks like 10, but I think it's 9.25. Is that right? I better just do that. I do have caffeine in front of me, but 9.75. See, there you go. Good thing I did that. So that'll be the shear. And so the next thing to do is to find that moment. And the way you do that is actually pretty easy as well. You know, just move that out of the way. Put a box around it. There's how you found your shear. Next thing is how do you find your moment? Well, the easiest thing is whatever point that he's wanting to see things about. In this case, he labeled it as C. Some of the moments about C. The reason to do that, or I like to do that, is because this way the shear never produces a moment about the point where it's applied. So that just gets rid of that completely. And then all you get is you get the moment. First, you get the moment. And hang on. So if I'm putting this, oh, here, let me slide it over. Equals 0 equals to the moment. Now, if I go back to my description where this is positive, then it appears to me like my moment's going the opposite direction. This is going the opposite direction. So I should have a minus moment. Okay, now looking at this force going this way, that's going to be minus 13.5 times the moment arm of 3/4. And then the other one is this 23 going that way is in the positive direction, 23.25, and it's 1.5 meters away. And so now you just move my m over. M is equal to 23.25 times 1.5 minus 13.5 times 3/4. And just so that I don't goof up, times 1.5 minus 13.5 times 3/4, 24.75. So if you think about it, these are the two forces. I'm sorry, not two forces. This is the force that you need to put right there. And this is the moment you need to put right there, so that if you did do all of this and break it all away, nothing would move. And so in the interest of checking ourselves, we need to know the number. F74. So I'm going to go ahead and do that. Let's see. Okay, so I brought up the new chapter, and it's down here. So I'm going to see if I can just take the appendix and move it down here, so it'll be directly under that. Okay. I don't know what that is. That must have been a problem I did one day. Oh shoot, I forgot the problem number. 74. Oh, F74. Okay. F's. Where? Oh, here's the F. Okay, so in the F's, he actually writes out the equations and does things. He did not do, oh yeah, he did. Here's this. He did the similar thing to what I did. He found the right end of that, 23.25. So my BY, 23.25, that number, or wherever I found it at, I don't remember. Oh, I found it right here. So he found that. Next thing he does, he goes in after the shear. Oh, okay, I need to make sure. So I just put that. I should have, okay. So if you subtract, okay, so if I should have moved, wait a minute, I have a positive shear. Wait, where it is? Up, down, and then over. And then I get a positive. Okay, I'll look back at that, but let me look back at that. Look at my moment. My moment's 24.75. And that's 24.75. So let me look at this for a minute. So we've got 13 down, 23. Oh, yeah. Why did I do it that way? So the shear and this, that means when this goes over, it becomes minus. So I flubbed up my signs there. So technically, when this goes over to the other side, it became a positive. When this went over to the other side, it became a negative. So that should have ended up being negative. There, you see, this is the part that bothers me sometimes. Before, he would, in the text, he would go ahead and put in here shear equal to 9.75 and point it, put an arrow down. That's not appropriate anymore. And the reason that's not appropriate is because you could be on the left end of the beam or you could be on the right end. And so at this particular point, you've got to stick to the sign convention. It sounds weird, but all of this procedure that he's been doing before doesn't work. Here's what I mean. If you took the right end of that beam and you took the left end, the shear actually goes like this, which means equal and opposite goes like this. So you could say shear is equal to 9.75 up here, and you'd say 9.75 down here. That's not appropriate. The key is the sign convention. This is your sign convention. So it's either in this direction, just like this, exactly like that, and it becomes positive. If it's in the opposite direction, it becomes negative. On beams and these internal loads, it's never appropriate to put the shears equal to 9.75 and have a direction, because it can be this way on this end and this way on that end. So you got to stick to the sign convention. And this is not a diversion, but something different. Before, if he found a load and found it to be, if he assumed it in this direction and he found a negative, he would flip the arrow and then give you the direction it was going. That doesn't work with this. And maybe I can explain why in a little bit, but, or maybe I should just do it now. I don't even know what time it is. I didn't even check. Well, wait, the stream is going because it's right there. Maybe I'll explain why here in a second. This might not make much sense, but it turns out, so this is a, what do you want to call it? Future. Well, I don't want to say, well, so we'll say in the future. In the future, in your future, that's not even the way you spell future. But in your future, you're going to take mechanics and materials, and then, I don't remember, there's another course and another course. And mechanics and materials is a very important course, and it spends a significant amount of effort on beams. And it turns out that a beam, what you're interested in doing, you know, I mean, just like the picture in the book that he had, well, beams are in structures everywhere. Bridges and buildings, we're sitting on a beam somewhere. It sounds weird, but the equation for the beam is this. This is going to look really weird. Equals to possibly an F load, where this F load might be a distributed load here. Now, what W is equal to deflection. And it turns out, you go one step back from that, you can get the, you know, so if you look at the deflection, so let's just assume we have a beam. Maybe it's supported here and here and here. I'm just making this stuff up. So the beam may go like this. So it maybe comes out like this, you know. There's a little support here. It's an awful drawing. But anyway, say the beam. So here's your support. This is pretty, this is the way it was before it got loaded. This is the way it was after it got loaded. So it's possible that you can put a load down, and if there's enough over here, you can have it lifting up. Just, it really does depend. But it turns out there's a term in here, and without too much explanation, and I'll give you some heads up on this later, this ends up being the moment. Somehow the second derivative of this function, which becomes the deflection as a function of f, becomes the moment. And then it turns out, and this E and I, you'll find out what this is. You'll find out what I is in maybe 2 weeks. You'll find out what E is. You've probably been introduced to E somehow, but you'll definitely find out what that is in mechanics of materials. And so the key is you're looking at functions that move from left to right. The second function will be the angle, so it'll be the slope. So you can have slopes to this thing. So if you look at that, and then you might want to come down and multiply times another term, the second derivative. So if you take the second derivative, so here you got a function, w dw dx, d second w dx. Now you can draw this, but you can also put an EI on front of it. It's a constant. Then it has a physical meaning. Then you can take a derivative again. Okay. And with that EI in there, it has another meaning. So what you're doing is taking a function, you're taking its derivative over and over, and you're going down to this. But believe it or not, you can go down to this, and if you want to go this way, you do integration. So in other words, if you had your load here, you can start, here's what I mean. There's nothing wrong with you doing this. Hang on. So this, sorry for my handwriting. And then you can integrate, yes, dx. And so you can move from the F to the W through a group of integrations. And this group of integrations you'll do in mechanics and materials in many different ways. Some of them are almost visual. So what I mean by that, if you're integrating just like what we did, if you want to integrate a function that looks like this, and here's your x, and here's your function, man, that's pretty easy. You just figure out the length, multiply times the height of that, and that area is the integration. And you can move up through that. So there are ways that you can do this that you don't have to carry out integration. But back to the point. The point is, that's why you can't arbitrarily change the signs here. There has to be a sign convention. Otherwise, you're going to, these are essentially what you might call boundary conditions. Maybe. Depends on the way you approach that. So this has a deeper meaning than just flipping the direction and pointing an arrow in the way that it goes. So, and you'll get a full taste of this stuff down here later. And my writing is 2 different sizes there completely. So that's a rough, very awful description as to why you have to stick to this sign convention here, because the problem is much deeper than where we are right now, and you just have to stick to that, and you have to trust that as time goes by, and it won't be at the end of this semester, but at the beginning of I guess it won't be the next, because the next semester is summer, so probably in fall. I don't know. Mechanics and materials might be offered. I have no idea. So sometimes it is. I don't know what time is it. Do y'all have any questions? I'll just come in and work more of these, more and more. That's what I'm here to do. So I guess I'll say we're done, unless you have a question. So when y'all came in, were the blinds already closed? Oh, okay. I was just wondering if y'all were going to try to like take a nap or something. Okay.